Welcome back. Today we're going to be exploring 2.03, putting it all together. Once we do that, you're going to need your booklet, a ruler, and an erasable pen or pencil. Opening up our book to 2.03, we're going to talk about putting together the concepts of multiplying and dividing exponents with finding how to reverse this process. So we're going to begin with a focus on something they've already done, which is multiplication. So taking a moment, multiply using the table method, that's otherwise known as the area method, 2x plus 5 times x squared plus 5x plus 1. If this is familiar, it is because we've done it before. So to multiply these two, I go 2x and 5 by x squared, 5x, and 1. And I multiply each term in turn, so that's 10x squared, 2x, then 5x squared, 25x, and 5. Summing along the diagonals, our solution is 2x to the third plus, got some more light going on here, plus 15x squared plus 27x plus 5. This is pretty straightforward. Now let's begin to connect it to some other concepts. How can you use this expression to quickly multiply the problem 25 times 151? The connection between these two problems is what would happen when x equals 10. If x equals 10, then 25 is the same as 2x, or 2 tens, plus 5. 151 is the same as 100, or 10 squared, plus 50, plus 1. This is not arbitrary. Polynomials are actually what you get when you want to work in any type of number system. So instead of going and multiplying this out, I can actually just take x equals 10 and substitute it into my equation, where it's 2 times 10 to the third plus 15 times 10 squared plus 27 times 10 plus 5. I can even take a moment, I can say, wait, if these are 2000s plus 1500s plus 27 tens plus 5, it becomes even more obvious how we connect them for a total of 3,775. How can a multiplication problem be rewritten into a division problem is how we're going to take this to the next step. A multiplication problem can be rewritten as a division problem. If I have a times b equals c, then I can in turn say that a must be equal to b divided by c, or b must be equal to, I'm sorry, it's not b divided by c, c divided by b, or b is equal to c divided by a. Now, we can do the same thing for polynomials. We can use what's called a reverse table method to determine the quotient 2x to the third plus 11x squared plus 7x plus 10. In order to do this, we should probably set up our table. And setting up our table, one thing I'm going to change about this, though, is I'm going to put the x plus 5 on this side. You'll see why in a little bit. It makes this the way you lay it out clearer. And here we go. Here's our table. And notice I haven't laid out the number of horizontal boxes yet, but watch, it'll begin to emerge. So I'm going to start with saying if my first box was going to be 2x to the third, then I know it was multiplied by x. So the thing that must have multiplied it must have been 2x squared, which means 5 must have been multiplied by 2x squared as well. Meaning that right there was 10x squared. Now if I look at my division, let's see, 2x to the third, whatever added to get to 11x squared must involve this 10x squared. So that means there must have been an additional x squared multiplied by here, which means x, what times x squared? What times x gives you x squared is another x. Bring that down here, that's a 5x. Well, if I had 7x in my result, that means I must have been getting 2x from the multiple for x, or 2. Then here, 2 times 5 is 10. that means it checks out perfectly. Or I've just determined that x plus times 5 must be times 2x squared plus x plus 2 must be equal to 2x to the third plus 11x squared plus 7x plus. What we just did is a very visual way of doing something that you're already pretty familiar with, which is called long division. The way we can relate long division with numbers, which you're already pretty familiar with, and long divisions with polynomials, is to recognize that each place value is the same as the power. So just as this 1000 is 10 to the third, we can also think about it as x to the third. So the same way we would go around dividing 1573 by 13 is the same way we would end up dividing x plus 3, because 13 is 10 plus 3. So we then generalize this or abstract this to say it's x plus 3 into the thousands, the hundreds, 7 tens, and 3, or a power of 3 plus 5 times the power squared plus 7 times the power plus 3. Let me get a little bit better focus on that so you can follow me as I explain. One thing I want you to invite you to do is pause and notice the pattern that's similar between these two expressions. Do you notice how what's outside is the same? That minus 13, minus 10, minus 3. What's left over is 2x squared, which is the 2 here. We again bring down the next number. And we keep asking ourselves the same question, very similar to what we did over here. If we have, how many times does 13 go into 15 once? How many times does x squared go into 3x? Well, x to the third time. How many times does 13 go into 27? Twice. How many times does x plus 3 go into 2x squared plus 7? 2x times, and so on and so forth. We can then in turn readjust that to be able to do a problem like, for example, here. Can we use a long division algorithm to evaluate 2x to the third minus 4x plus 2? Now, just a reminder, what's below is down and out. So it goes on the outside of the division. Then 2x to the third minus 4x squared plus 0x plus 2. I always like to add the placeholder because otherwise I'll often make mistakes about lining everything up. And so I'm going to ask myself the same kind of question I would ask if this was like, for example, 22 going into, let's see, that would be 2,402. So how many times does 22 go into 24 is once. How many times does 2x minus 2 go into 2x to the third minus 4x? Well, I would have to multiply this by x squared, or 100. Notice that's a power 2. This is actually going to be a power 2. So let's see, guys, it's going to be 2x to the third minus 2x squared. Same thing I would have here. Now here the leftover is clearly 2. Here when I subtract the terms, let's see, notice something interesting is going to happen. Because this is negative, it's going to be negative minus minus, so that's plus. So negative 4 plus 2 means a remainder of negative 2 squared. That doesn't show up here because we almost kind of assumed here. Right? If this would be like, if we could make a place here negative, that would work. Then we bring down the next term. Notice it's a placeholder term because there's no x squared there. Then we ask ourselves, what times 2x minus 2 would give us negative 2x squared? Let's see, that would be a negative x. So negative 2x squared, so negative x times 2x is negative 2x squared. Negative x times 2 is plus 2x. Subtract. Well, these two will cancel, and 0x minus 2x is minus 2x. Bring down the last term. When we bring down the last term, what do I need to multiply that divisor 2x minus 2 by in order to get negative 2x plus 2? That would be negative 1. And when we multiply that, subtract, we have no remainder, which is amazing. Now, as we practice this in class tomorrow, take your time and some extra paper to write these all out. It is often helpful to kind of write the equivalent number method and remind yourself how you would do that problem. But always be aware of if you have negatives in your polynomials, it would be like you're subtracting out than just a straight up replacement. Looking forward to this practice with you. I'll see you there. Closing out, and have a wonderful rest of your day.